Okay, let's start. I'm Alex Bronstein. This is a class on deep learning on hardware accelerators. Uh, and this is kind of an ongoing experiment. Actually, I didn't expect to see such a big class. Um, but anyway, I will tell you a little bit about the course in a few minutes. So I will just say two words about myself, why I believe I qualify for talking to you the entire semester about deep learning. So I did my all my degrees here at the Technion, masters in electrical engineering and then PhD in computer science. I've been faculty in the WE department at Tel Aviv University and then moved back to the Technion essentially in 2016 here to this faculty. And my research interests are mainly in computer vision, image processing, imaging, signal processing in general. And since these disciplines have become or degenerated, depending on your point of view, to be applications of machine learning and deep learning recently, that's why in the past decade or so, I have been heavily using machine learning techniques and deep learning in particular. I also had a few industrial adventures. I've been a founder of 3 startup companies until now and served in different capacities in a few others. And I've been doing hardware, software algorithms, and a lot of machine learning in all of them. So I guess I can also see some practical sides of this technology as well. A question, please? So the microphone is for recording this talk. I don't think it's connected to the audio system here. And obviously, so as the name suggests, we'll see some hardware, some computer architecture components in this class, and for that, basically, I'm joined in this course by Avi Mendelsohn. He's a very well-established computer architect and expert in computing systems and computer architectures, who is going to be your instructor in that part of the course. We have a stellar team of TAs. Chaim Baskin and Aviv Rosenberg, they are both PhD students in our lab. And Evgeny Zheltonovsky, he is going to be responsible for the home assignments and also projects in the course. Now, as I said, this is an ongoing experiment. This is the 3rd edition of the course, and this semester we are going to try offering it in the flipped class scenario, in the flipped class version. And flipped class means that we work less, meaning that we made this effort to record the lectures in the last semester, so we have full set of video recordings, and you're going to watch these lectures at home. And arguably, this is a more comfortable setting, especially because there will be some amount of math. It is much easier to follow the derivations in the comfort of your sofa rather than sitting in a class. So at least this is my own opinion. You can disagree, but we're going to try it. And then we'll have more free time in class for interaction. So we can discuss things that maybe are not clear or require some additional discussion in class based on what you have seen in the video lectures. And I can also have some more time to show you more advanced stuff, or maybe to show you some preliminary, some background that I don't know, that might require some deeper discussion. So we'll see how it goes. Of course, I will be happy to receive real-time feedback as we proceed. Again, we are learning together, so how to do it in the optimal way, and you'll see that all this class is about optimization. So this part will also be optimized end to end. I will give you every time. Again, this is how I would like to structure this course, but maybe it will change during the semester. I would like to give you some. So at every week we'll meet in class. I will show you some brief introduction to what you are going to see at home in the video lectures, and I will assign you a certain chapter in the video lessons to watch at home during that week. And then we are going to discuss basically some and maybe expand on the topics that you have previously seen. So please don't procrastinate and watch the assigned lectures, because otherwise you will be lost. Okay, so again, in class we are going to discuss the previously assigned lectures and going to introduce some stuff or maybe some background, some material for what you're going to watch next, basically in that week. So from that perspective, it's very convenient that we are meeting on Sundays. So you have the entire week to watch the videos. There is no exam in this class, meaning that you'll have to work. So we have 4 home assignments, each of them constituting 10% of the final grade. And coding home assignments, I mean actually coding. Lots of coding, though we tried, and this is mainly thanks to Aviv, to structure the exercises in such a way that some code is already written. And actually it's written quite well. So it's basically, you can also learn from reading this code, but you will need to fill it with your own, with the product of your own creativity. And basically this will be 40% of the grade. I believe that this is the best way to learn something practical. So the idea is that you, by the end of this course, you will be able to use the tools that we are trying to sell you here. And the remaining 60% of the grade will be a final project, can be submitted, actually must be submitted in pairs. And the projects we will talk more about the projects sometime toward the middle of the course. We are going to assign you a list of papers, basically state of the art in this domain, and you're going to do projects on these papers. If you have your own crazy idea in mind, of course, be our guest. If it is adequate in terms of scope and amount of work for the project, it can be a substitute to papers on our list. There is a dedicated course website. We are putting all the materials, lecture notes, presentation slides, links to the YouTube channel, videos, assignments, announcements. Basically, everything is on this web. There is a YouTube channel that I'm keeping actually a YouTube channel dedicated for video recorded courses. There are several courses, including this one. If you subscribe to the channel, I'm going to record from time to time things that we do in class, if I believe that they worthwhile being watched afterwards. And I'm going to upload them to the YouTube channel. So if you subscribe, you will receive regular updates. And of course, all the videos will be linked to the website. We also have a Facebook group for informal discussions and matchmaking for projects and so on. Since the type of programming you're going to do here requires a considerable amount of compute power, we have dedicated HPC servers, dedicated machines with GPUs that you're going to use. Basically, the access instructions are on the website. Of course, the TA team will make sure that you know how to run your code on these servers before you start writing anything serious. So this is a must. Okay, so these are the formalities. Of course, if I forgot anything, there is more information on the website. You're welcome to disturb us by email, obviously. So anyway, these are the formalities. So let me show you some motivation or some propaganda of what we are going to see in this class. And I guess artificial intelligence is a horrible name because it's used appropriately and inappropriately in all kinds of contexts. But basically, I think in the past probably 10 or even 5 years, this is becoming one of the dominant discussions in different forms, not only in technological forms, but also in policy making communities, in even among philosophers, basically. Is it true that we are at the verge of creating artificial intelligence? And I'm not going to answer this question. So it depends very much on what you mean by that definition, but you can clearly see an explosion of AI, or basically machine learning based technologies around us, different applications that have been practically revolutionized by the recent advances in machine learning and artificial intelligence. And probably one of the most prominent ones is the self-driving cars. So today I think it is quite obvious that it's just a matter of time until we see all our vehicles replaced by self-driving vehicles, by autonomous vehicles. And if you estimate the economical impact, of course the impact on society will be profound, but just the economical impact, something that you can state with a dollar sign, just the amount of time that will be freed by not needing to hold the steering wheel anymore will amount in our generation to something like $7 trillion. Basically, a new economy will emerge out of this new time. So this is incredible. This is basically a world-changing impact. Similar impact will be also, basically, we are already facing it in the domain of digital health. It can replace doctors and maybe even some procedures, some medical procedures, again in our generation. We see around all kinds of smart wearable devices and home assistant and smart home and home automation technologies that try to alleviate some of the burden of our everyday tasks. We also see an explosion of video surveillance technologies. I think in the past 5 years, incredible amount of progress has been done there, and especially this is especially commonplace in countries where privacy hasn't been such a big issue, like China, for example. We also see incredible progress in applications like machine translation. So today, if you couple this technology with computer vision and augmented reality technologies, you can just point your AR glasses or your smartphone to a sign written in a foreign language, and it will replace the characters and the text with the text that you can understand in your own language. And this is something that maybe science fiction writers could envision a few decades ago. Now it's practically reality. You can use it yourselves. It works. It's far from being perfect, but it works. There is another very much PR'd achievement in this landscape of AI. Basically, the AlphaGo system that was developed by DeepMind, the Google company, that defeated the world champion in the Go game. Go is considerably more complicated than chess, and that was very much discussed and very much PR'd piece of news. But then about a year afterwards, another technology, another version of this system emerged that was called DeepMind AlphaGo Zero, that probably received less acclaim in the press, but that was a real revolution from the following perspective. Basically, unlike previous systems, like for example, machine chess players that were designed by humans, that contained lots of domain knowledge of our human experience in playing the game, basically the AlphaGo Zero, and basically AlphaZero in general, that for example the chess player was basically, it was it's not just, it's a lot of intelligent design being deployed there, but it started with a neural network, with an artificial neural network that didn't know how to play the game. So it learned how to play it out of nothing, out of playing with itself. The only domain knowledge that the system knew in the beginning of its training are the rules of the game. Basically how the game is structured. All the rest emerged from playing with itself. So maybe some people will say, but you cannot match the creativity of human players. This is bullshit. So I cannot talk about Go, but I can say something about chess because I know how to play the game. If you just watch at a few matches that the AlphaZero chess player played, you have never seen anything coming close to it, anything similar played by any human in the whole history of chess. So if this is not creativity, what else qualifies for this term? So I think it is quite amazing, and of course this is a bleeding edge field. Basically, we see more and more innovation coming from from the industry and from the academia, from researchers around the globe at a very fast pace. So maybe in a few years, what we are talking here will sound like archaic and outdated technologies. Probably it will. So you can wonder why. So we will see mathematical details. You can wonder why what we are discussing. So why is it so successful? Why is it so new? You will see that the algorithms and the techniques that we are going to discuss, they are not exactly new. At least at the principal level, they existed decades ago. So why now? Why not before? Why are we facing this explosion, this spectacular success of deep learning? And I think there are two main ingredients to it. One of them is what is referred to by the buzzword of big data. So this is just a simple synopsis, a simple statistic of what happened in terms of data consumption and production in a single minute in 2017. So in 2017, in 1 minute, 3.6 million searches went on Google. And YouTube users watched over 4 million videos just in 1 minute. So just imagine how much data, so basically how many petabytes, or I don't know what is the next prefix for such quantities. The Weather Channel received 18 million forecast requests just in a single minute, and over 100 million spam emails were sent in a minute. So these are really humongous quantities of data. Again, this buzzword, big data, nobody really knows what it means. So I will give you my definition. It is as good as anyone's else. So my definition of big data is more data than you could ever hope to be able to use. Okay, so you are flooded by data. So you have more than you could use. And actually, this is becoming some kind of practically the importance of data. Someone compared data to the petroleum of the 21st century. I think you cannot have a better definition than that. I think it is being elevated to some kind of a religious creed. So basically, the being connected, being up to date, being connected to the most up to date source of data becomes almost an obsessive necessity in our society. And I think I cannot refrain from quoting from Yuval Noah Harari. He has very sharp opinions about different matters. I share most of them. But so he writes specifically about data, and he wrote like this: just as divine authority was legitimized by religious mythologies and human authority was legitimized by humanist ideologies, so high-tech gurus and Silicon Valley prophets are creating a new universal narrative that legitimizes the authority of algorithms and big data. This novel creed may be called dataism. So he essentially believes that we live in the epoch of a new kind of religion that is based on data. So definitely this deluge, this plentifulness of data is one of the driving forces for why we see such a spectacular success of AI today and not, let's say, 20 years ago. Another reason is the compute power. Okay, so we'll see that for actually deploying, for actually using these algorithms, especially when you need to crunch such humongous amounts of data, you need strong computers. And in 1970, Gordon Moore, one of the founders of Intel Corporation, predicted that the number of transistors in processor chips will grow exponentially, will double itself every 2 years. Then these 2 years was updated to 18 months. And you can see that despite the fact that the number of people who predict that Moore's law is dead doubles itself every 2 years, you can see that there is a steady exponential increase in the number of transistors in different processors on the market in the past 40 and something years, as Moore predicted. So basically, we have an exponential increase of available compute power that we have under our fingers. So combined, these two these two significant drives created an ecosystem in which we can talk about practical machine learning or AI applications. There are many problems or tasks that can be individuated in this domain, and recently all of them have been spectacularly solved by a class of methods that is called deep learning. Okay, so of course everyone here heard about deep learning. So deep learning is the new hype, the new revolution. And actually, just to show you a few examples, for example, if you take visual recognition, you take as the input a bunch of pixels constituting a digital image, and you would like to tell what is inside, what is there in that image. Is it a chair? Is it a table? Is it a car? Is it a face? Basically, this is the hallmark of computer vision: recognize what is there in an image. And computer vision has been a storytelling discipline of computer science for many years. So basically, you know how to explain everything, but nothing works. I come from this domain. I can attest to it quite surely. So people have been progressing quite steadily, slowly, with improving the recognition rates. There has been infatuation with different types of models in different times. From 2010, when the ImageNet benchmark has been created, there is a standard way of reporting your performance on visual recognition tasks. So here you say some misclassification rate, some error rate. The lower the number, the better. And you can see that there was a steady progress. Again, at least on this benchmark, there has been a steady progress. In 2012, you suddenly see a result that doubled, or that halved the error rate, that doubled the performance of existing visual recognition algorithm. And this is the first time deep learning has been used for this task. And basically, since then, there has been a steady progress. Currently, at least on this benchmark, machine learning systems work better than humans. Okay, so they make less mistakes than typical human observers. A very similar situation. So practically, you can take any domain, you will see this. You will see this trend. Another example is speech recognition. Actually, deep learning has been it is renowned as a career breaker for in many domains. Has ruined many careers. It happened to me to talk to a very senior engineer from one of the corporations that has spent his entire career on doing speech recognition, and he told me that basically I declare bankruptcy. Today, a student with zero domain knowledge in speech in 1 week or 2 weeks by just training a neural network can do better than anything I have ever created in my life. And this is typical to many other domains as well. So to the extent that we can start talking about, or maybe we can stop talking and start using a new paradigm, a new approach, a data-driven approach to the way we conceive of programming in general. So call it software 2.0, if you will. Basically, it's a data-driven approach. And you can argue that in many real-world problems, it is much easier to identify some kind of desirable behavior rather than explicitly write code that implements that behavior. And of course, we'll see plenty of technical examples. Let me just give you some very human example, very non-technical example. So for example, I can go to a museum and watch a painting by Vincent van Gogh. And let's say I have some skill with a brush. I can even try reproducing it at my leisure at home, probably with some success. But I cannot conceive of imagining myself and creating a painting like that out of nothing. I can go to a concert hall and see some fine pianist playing, I don't know, Chopin's Prelude or Beethoven's Sonata. I can play it on my piano, but I cannot compose music like that, not even close. So somehow, basically, if you formalize it enough, probably it will tell you that P is not equal to NP. So it is much more complicated to create something rather than validating that something is good. Okay, but basically we can use it as a way of programming our machines. So if you think in some kind of abstract terms, a computer program is a map between some space of inputs to some space of outputs. Okay, so then you imagine another abstract space in which every program, every map of this kind is a point. Okay, so you have a space of programs, a space of maps. Okay, and now you can try playing the following game. Let's search in that space of programs for the program that implements in the best possible way the desired behavior. So if you can mathematically formulate in terms of some quantifiable criterion what it means to produce good behavior, then you can try searching in the space of programs for that magic program that gives you the optimal performance in that sense. So we will see, of course, how to reduce it into practice, but what is amazing that it works. What is amazing is that we will see that this results in huge optimization problems that are, at least theoretically, if you ask a mathematician, they are unsolvable. They are unsolvable. We have no algorithms that will guarantee that we find a solution in observable time that, at least in some strict sense of what solution means. But practice shows that solutions that we obtain are still usable and useful. Okay, so essentially this new paradigm, this software 2.0, means that instead of explicitly understanding how your world works and then reducing that domain knowledge into some computer code, you actually learn that code from examples. Okay, so this is a paradigm shift. This is different from what we have been learning in programming classes, right? This is completely different. And this is, of course, our main workhorse, our main instrument will be neural networks. We'll see different types, different so-called architectures of neural networks that will essentially be our programs, our new form of computer code. But you can also take more abstract constructs in programming languages like function calls, like stack, for example, different types of behaviors. You can make them differentiable, and differentiable means that they will become amenable to that kind of a search process that we are going to use to find the best program in that space of programs. Okay. So again, this is something that you could conceive of 50 years ago, but it was useless in the absence of data. Now, once we have data and we have enough compute power, we can actually not only conceive of such an approach, we can actually use it. Okay. Now, what are the advantages on the practical part, at least from the system perspective? From the system perspective, using neural networks has the advantage of using a very narrow and homogeneous instruction set. Essentially, you use multiply and accumulate and some simple nonlinearity instructions. Because of having such a reduced instruction set, it is much easier to port it across different platforms. It is much easier to reduce it into hardware. You will have, for example, predictable latency and memory use and balance of different computational efforts going on in your piece of hardware. The data will flow in a very regular way, which means that you can design very efficient memory systems and remove many bottlenecks that you would otherwise see in other types of computer code. This approach is also more agile. For example, if you are not satisfied with the performance of your visual recognition system, okay, increase the size of your neural network, train it for more time on more data, and voila, you have better performance. Okay. So now imagine in the classical approach to programming, if you, for example, need to do a Fourier transform, you have a certain algorithm that does a Fourier transform and you want to make it faster. How exactly do you do that? There is no recipe. You cannot go to a recipe book and tell, well, I want, instead of n squared, I want n log n. How exactly do I do that? That requires a strike of a genius. For example, one of the 10 most important algorithms that have been invented in the 20th century is the fast Fourier transform, FFT. there is no recipe, consistently repeatable recipe how you invent this type of algorithms that improve your some performance criteria in that sense. For example, the computational complexity. With the data-driven approach, you have a much cleaner and repeatable and consistent ways of being agile. Okay, and actually, when you build real systems, they comprise multiple modules. Each module can be designed and trained and tested and validated separately, but then you combine them into a single system, and you see that you have some performance bottlenecks, and it requires optimization. So this approach allows you to optimize an entire system end to end. If you have enough time and compute resources, you can optimize an entire system end to end. For example, if you are building a camera that really is needed to recognize faces, maybe you don't even care about showing a nice picture to the user. So then you can optimize even at the level of optics and the sensing electronics. You can optimize all the system end to end until you hit that goal, recognize faces. And basically the emerging field of computational photography is just about that. And you cannot do it in software 1.0. It is completely infeasible that you optimize, let's say, your network drivers and your display drivers when you want to get 10% faster response in your Google Chrome browser, right? This is completely nonsense. But you can do such things when you use the data-driven approach. Okay, and the most important reason why to use this is because the software that you create, I wouldn't dare say, right? The software you create this way performs better than you and I can ever hope to build. Okay, so you can try doing something handcrafted, but what you will find by these automatic search processes will be better. And today in this community, the word handcrafted sounds like something antediluvian, something it is used in a derogatory sense. You are using handcrafted features. Come on, man. This is archaic. So basically, this nobody uses anything handcrafted. We are trying to learn everything end to end, and as long as we have enough data and enough compute power, this is possible. Now, this sounds too good to be true, right? This sounds like this is the magic bullet that can solve all the problems in computing, right? So basically, you have this new magic tool for writing software, but it comes with many disadvantages, obviously, like everything in life. So one of the main disadvantages is that we have no clue why this works. So it's a big disadvantage, right? So well, maybe let me try seeing slightly smarter. It's not that we completely have no idea why it works. We have some idea why some things work. Okay, there is no one big theory that tells why deep learning works, how to make it better. For example, how to select some meta parameters of a neural network, how to select the number of layers, the configuration of layers. There is no theory that will tell you how to do it. There are some useful and working and efficient industry practices, but very far from some kind of solid theoretical foundation. Okay, so you have to accept this. And some bad tongues will even say that the state basically the current state of affairs is more or less comparable to alchemy. Okay, so we are doing alchemy essentially. This is not science. This is alchemy. And well, of course I pretend to be a scientist, but I come from the applied world. So if it works, then okay, let's use it. Let's maybe try to understand why and how. But the most important thing is that it works, and it's very hard to argue with something that works. It works. And same about alchemy. So if you go to this analogy, I don't see this as an offense. So alchemists were dead wrong about 99% of the things that they claimed. So today we know that it takes a nuclear reactor to transform lead to gold. But occasionally they discovered some important things, like for example, redox reactions or conservation laws. fundamental things into the edifice of chemistry and physics that we have today, and that would be impossible without that alchemy, right? So even if we're doing alchemy, it works, it can do something useful, we will replace it by something better. So let's work on that something better, but let's not ignore something that is useful. Okay, so I would like to adopt this approach. So if you don't like this approach, you can of course leave it, but unfortunately I cannot offer anything better than this. So that's why I'm targeting this as a very practical class. And obviously there are some results coming with a very fast pace that also give pieces of theory and theoretical understanding of why some things work or why some things are wrong, actually, even if they work, and how to do them better. So because we are using some kind of a machinery that we don't fully understand why it works, it also comes with some perils, some dangers. For example, there is this visual recognition system that is called Inception. It achieves practically something close to the state of the art on the ImageNet recognition task. It works really well, much better than humans. But when you input this video with this funny looking turtle as the input, it will recognize it as an assault rifle. Okay, so do you see an assault rifle here? No, it looks like a turtle, but the system sees an assault rifle regardless of the vantage point. Okay, so from every angle it will look like an assault rifle, and you can say, well, oops, that's unfortunate. That's a shameful mistake. But this is not a mistake. Actually, this turtle has been engineered on purpose to fool the system. Okay, these are called adversarial examples, or it's not an example; it's an adversarial attack. This is a vulnerability of a computer system, and you can exploit it. You can attack this system. So imagine, it sounds really scary. It's scary. Imagine your autonomous vehicle, and you fudge a little bit something in something on the road. You place some sticker on your road sign, and then it crashes or does some horrible things. So it's a real danger. It's a new kind of vulnerability. It's a new kind of threat. So we more or less understand why this threat exists. We don't really know how to recover from it to some reasonable level of performance. Okay, so we'll discuss it, why exactly this happens, and how to defend deep networks from this kind of adversarial attacks. But there is no panacea, that there is no cure that will bring you back to your desired performance. So we need to be aware of that, and because we don't know exactly what happens inside, we might be unaware of some other threats of this kind. Okay, so this is the danger of using something that you do not completely understand. Okay, but we still use our own black box that we don't fully understand, and we find it okay. So we find it okay to rely on human performance, on human decision-making process. We know that it's really, really bad in many situations. Okay. So if you accept this situation, I think then you will also accept our declared goals. So I would like you to learn hands-on, and that's why you will have to write many lines of code. I would like you to learn hands-on a set. Let's think of it as a representative, as some kind of basic tool set of many modern deep learning techniques. There are two principal packages that are used today in the academia and the industry, one of them being PyTorch, another one being TensorFlow and Keras. We selected PyTorch. This is just an arbitrary decision. Of course, the other one is as good as the first. And at least I'm not going to pretend that I understand why these techniques work. I will still show you some theoretical derivation and some results. So we'll do some mathematical exercises. And since we live in a real world where essentially everything runs on some piece of silicon somewhere down there, I would also like that we understand the hardware implications of everything we build. Okay, and that's why we are going to talk about the hardware aspects as well. Okay, so I will show you some overview of the course topics that we are going to encounter in this semester. So first of all, we will talk about neural networks, how to train these data-driven models, both the science of it and the art of it. Some industry practices that maybe still elude some solid theoretical explanation, and we'll talk about optimization methods, and specifically about stochastic optimization. We'll see that the good old chain rule that you hated in high school, this will be our main tool. Basically, practically the most complicated piece of math. Well, I'm joking, but one of the main pieces of math that we're going to use will be the chain rule, how to find derivatives of nonlinear systems of functions. We'll see, since we're dealing with numerical methods that need to solve big optimization problems, we'll see the numerical problems that will arise, like vanishing and exploding gradients, and how to try to mitigate them or how to cure them. We'll talk about activation functions, about initialization, about different methods of regularization. That is the alchemy part. About data augmentation techniques. So basically, these are just buzzwords, but you will see that there are some ideas, or sometimes no understanding, but still it works. But basically, there is some evidence behind them. We'll talk about what is called deep neural architectures. Basically, think of architectures as different ways of structuring your computer program 2.0. We'll talk about multi-layer perceptrons, or fully connected neural networks in the modern language, convolutional neural networks, residual networks, recurrent neural networks, long short-term memory networks. We'll talk about gating and attention mechanisms, and many other aspects of modern deep learning. We'll also learn about different types of learning regimes or learning settings. So probably the most popular and the most used one, arguably, is the supervised learning regime. So suppose you have a classification task, you have some input, for example, an image of a cat, you have some program that receives this input and produces a label of a class. And let's say this program sees a cat and it thinks that it's a dog. Okay, so then you can take the error, the difference between the ground truth label and the predicted label, and you can tune the parameters of this system in such a way that it finally learns what a cat is. Okay, so this is the supervised learning. So you have some label, you have some supervision. Then we'll talk about the unsupervised setting, and the unsupervised setting is essentially learning how to generate data. So you don't have labels, but you will be able, for example, to take the image of a dog, squeeze it in some way that only the essential amount of information remains, and then from that amount of information, reconstruct the image. Okay, so if you are able to do it, then the representation that is created in this bottleneck of information can be used as some kind of latent representation space. So you don't know what it is ahead of time, but you learn it from the data, and you don't need labels for that. Of course, we will see all the mathematical setting for these problems in great detail. Currently, I'm just trying to give you my marketing pitch. Okay, so this is unsupervised learning. And today, more and more techniques manage to switch from the supervised setting to the unsupervised setting. And you can argue that we humans, we don't really learn in the supervised regime, at least in the canonical definition of this term. Okay. We'll also talk about, again, talking about generative models, we'll see what is called generative adversarial models, or GANs, generative adversarial neural networks, essentially ways to train generative models that produce distributions of data that are indistinguishable from distributions of real data. And how do you decide whether a distribution is indistinguishable or not? You play the following game. So I'm a forger, and I'm trying to forge an image in such a way that it will look indistinguishable from a real image. And I will put a detective, another neural network, essentially, a discriminator that will try to detect the forgery. So that this discriminator will try to distinguish between two piles of data, the ones I generated and the ones that came from a real data distribution. And my generative model will try to fool the discriminator in the best possible way. So by playing this kind of adversarial game, today we achieve state-of-the-art results in generating images and other types of data. And for example, today you can generate human faces that no human will be able to distinguish from real pictures of human faces. Okay, quite amazing. We'll talk about domain adaptation and domain alignment and transfer learning, at least in some extent. I'm giving you all the examples with images, so let me give you another example. So suppose let me give you a human example, and basically essentially we'll try to recreate it on a machine. So suppose I learned how to sing, let's say, and can this knowledge be of any help, for example, to learn how to play the piano? Probably yes, right? So there are some rules of music that can help me to that I can leverage from my singing lessons. And when I know how to play the piano, probably mastering the guitar will be an easier task than doing it from scratch, right? So somehow I'm transferring my knowledge about a different musical instrument to a new task. Okay, so this is called transfer learning. Or you can take it in some more restricted setting. I have, for example, data that looks, for example, like this piano score, and I have this guitar tab. These are different types of data. They are different objects. But maybe I can leverage my knowledge of how I treat these piano scores to better understand guitar tabs, right? So if this analogy speaks to you, but anyway, basically I can try to leverage knowledge that I gained for one task in order to better solve a different task. Okay. We'll also talk about a setting that is called reinforcement learning. So imagine we have some agent that acts in a world, like an autonomous vehicle, for example, and as a result, we receive some kind of a reward signal. So for example, if I haven't crashed yet, then probably it's a positive reward. And if I crash, then it's a negative reward. So can I learn the optimal behavior of this agent, how I drive my car, in order to maximize my reward? So I want to get from point A to point B in the fastest possible way without killing my passengers, right? So this is my reward. And I don't know my environment. The environment is unknown. It is also unpredictable because there are other agents playing in it. So this is how, for example, the Go or the chess game is approached with modern deep learning tools. So we'll see that if we put a deep neural network on the agent side, it will be able to both discover the rules of the game and find the optimal behavior. Okay, so this will be our setting for reinforcement learning. We'll see many applications, some of them in the lectures, some of them in the tutorials, in the exercises. We'll see many applications with working with pixels, with images. For example, how do you take a low resolution image and produce a high resolution image? So if you, for example, if you are a fan of CSI movies, CSI series, so you can probably see this scene multiple times, that you see on the surveillance camera screen 2x2 pixel image, and they say zoom in, zoom in, zoom in. Oh, I know this guy. So of course you cannot do anything like that, but not very far from it. If you have enough information, enough prior information about your class of images, for example, like this is a face, you can hallucinate details, and they will look realistic. Of course, no forensic guarantees, but they will look realistic. Okay, you can also do image processing in general. So for example, in this smartphone, there is quite a complicated piece of hardware that processes the raw output of the image sensor until what you get on the screen. You can do it end-to-end by learning, and you can do denoising, demosaicing, and different image processing tasks, deblurring by doing deep learning. You can also do completely crazy things that even 5 years ago it was not even clear how to how to formulate them mathematically. So we don't know how to formulate them mathematically even until today, but there is some clever hack that works. So imagine that I took that picture of some canal, I think in Amsterdam, and then I give you one example of some work of art. For example, this, let's say, this work by Van Gogh, or this work by Edvard Munch, and I would like your image. I would like you to generate a new image that will be structurally similar to the input, but it will be painted in the style of Van Gogh, let's say. Okay, and these are the results, completely automatic from a single example of style. So you cannot really define what Picasso's style is in terms of equations, right? But you can collect some statistics from the workings of a neural network, and then use those statistics to compute a new image that will coincide with them and will be similar to your input. We'll see exactly how to do it mathematically. This is called style transfer, and again, crazy application. You can find it already in forms of apps on your smartphones. It is driven by this kind of alchemy. The hallmark of computer vision: segmentation and semantic segmentation. So segmentation means that you know how to distinguish foreground from background, and semantic segmentation means that you also know what that thing is. So it's visual recognition plus segmentation. So segmentation has been like the most challenging problem in computer vision, and with today's tools you can solve this problem finally. Of course, still a lot of work to be done, but for example, this is what your camera installed in your vehicle sees, and you can segment the scene into pedestrian, vehicles, buildings, road signs, and so on. It is quite amazing. Didn't work until, let's say, 5 years ago. We'll talk about some applications in natural language processing. How can we program the machine to understand human language? How can we understand, for example, the emotional charge of a phrase? Is the guy pissed off? Is he happy? How can we tell that? Because maybe he's using irony. He's saying, "I've never felt better before," but he's angry. He's unhappy. So how do we do this? How do you do machine translation? The grammar is different. The order of words is different. There are ambiguities in human languages. So we'll see these tasks. We see how do you represent a phrase? How do you represent a sentence? It's not an image. It doesn't, for example, have the same number of elements in it. So we'll see that there will be appropriate models to deal with language. It's not a course on NLP, on natural language processing, but we'll see some elements of NLP and related deep learning tools. I will also show you some elements of how to deal with more exotic but still very important types of data. For example, take a social network like Facebook. It's a graph. It's a graph. It doesn't have the structure of an image. It doesn't have a Cartesian grid with pixels. It's unstructured. Okay? But still, there is a lot of information in that structure. And actually, you can say that all the information is in that structure. You take, for example, a protein-to-protein interaction network. Also, there is a lot of information in that graph, in that topology. Can you, for example, predict how a certain protein will interact with other proteins? If you do, you can design new drugs. You can design new cures, right? So that is important. When you, for example, when you talk about autonomous cars, you use more complicated sensors than just regular RGB cameras. You can also build sensors that sense depth. So every pixel in your image will also tell the range, the distance to the object. What you get as the result is a cloud of points in the three-dimensional space. It's not an image. How do you deal with it? So how do you deal with this kind of non-Euclidean data? We will see that the main workhorse that we will call a convolutional neural network can be generalized, in part at least, to these kinds of more complicated non-Euclidean data. Okay? We also talk about reinforcement learning, about autonomous agents, how to teach the machine to play a game. Okay? We'll talk about the hardware sides, hardware accelerators, elements of parallel computing. We'll specifically talk about GPUs as a tool to accelerate training of neural networks. We'll see elements of CUDA, which is the language for programming GPUs, directly in Python, in PyTorch. It's a very useful tool. If you want to accelerate some exotic type of calculation that you don't have library support for, be my guest, program it in CUDA. We'll see different types of hardware, emerging hardware that is used, is being manufactured, is being designed for hardware inference. We'll see what it means to make your neural model efficient on hardware. We'll specifically talk about low precision arithmetics, how to do quantization of neural models, how to do knowledge distillation, to pack a big model into a smaller one, teacher-student models, and basically different techniques that have been proposed for these tasks. And again, this is a moving target because the state of the art is always moving forward. Again, I will remind you about these online resources. So basically all the, or at least the majority of the material that we are going to be use in this course is already online. You can watch the videos, you can read the lecture notes, you can see the presentation slides. And again, this is an experiment. We'll see how this flipped class idea works. So what I will ask you to watch for the next week is another introduction that Avi Mendelsohn prepared for the hardware aspects of this course. You can actually defer it to the second part of the course, but just to start hitting the engine, so to say, and watching the YouTube videos, start with that part, prepare it for next week. Then what I'm planning for next week, I will show you some brief introduction. So we'll essentially, I'm not a big fan of formal prerequisites. So I don't care whether you took probability classes or some other classes. I will try to make everything self-contained, but still, I mean, some ABCs are required, and our main requirements will be, we'll need some notions of probability, we'll need some notions of calculus, vector calculus, and linear algebra, just to know what a norm is or what a conditional distribution is, okay? So our first tool that we are going to use heavily just from the first lecture is going to be probability. So I will prepare some very brief reminder of what conditional distributions and other stuff are. There is a written basically crash course on probability, set of basically basic notions that is published on the web. I will still prepare something for the class. I will record it, put it in YouTube, just in case you prefer a narrated presentation rather than just reading a lengthy text. And then I will show you some elements of basically some kind of advertisement of the first chapter that we are going to learn about supervised learning. So I will show it to you next week, and you are going to watch the details on video. Then we'll have a discussion. I will show you some more advanced stuff. I invite you to have an interactive discussion here in class, and then we'll move to the next topic. And we'll see how it works. We publish some tentative schedules, some tentative syllabus, basically on a weekly basis, what we are planning for this class. Of course, I'm sure we will deviate from it. I hope to the best. And I invite your feedback basically in real time. Don't wait for the last lecture of the course to say that something sucks. Okay? Anyway, thanks, and we'll adjourn at this stage. I'm not going to use all the 2 hours we have assigned in class because of the video lectures. Otherwise, it would be unfair to ask you to watch 2 hours at home and then suffer another 2 hours in class. But we'll try to use it creatively, okay? Thanks.